Hey, John here. We know how to compile a freestanding program, at least an assembly language program at this point. Let's get to the point where we can run a regular C program and include a bunch of standard library functions along with it. All right, so we're going to go through a couple of examples and build it up from the basics here. Okay, so let's start with this little program here. All right, now let's go ahead and open it in the editor. Easier to see what's going on. Now, according to the rules to boot up a freestanding program, it's our responsibility to clear the BSS segment out and set it all to 0. And that's what this code right here is going to do. And this code is written without the pseudo operations, okay? Now, I wanted you to see what this looks like if you had to write it all out by hand. Let's start with the beginning here, this set GP register stuff in here. You'll see that what's happening here is these are the guts of the LA pseudo operation. All right, so if you don't have that, you don't want to use it for some reason, you have to get the high part of the address based on the label and then the low part of the address. Okay, and you can see the LAPC and the add immediate, just like we were talking with the LI and the LA pseudo operations. Okay, down here, what is really happening? We're trying to find the end of the data and the beginning of the BSS. So it gets really noisy if you have to write all this stuff out longhand, is the point, all right? And then we go into this loop down here. We put 0 into register A2, which is X12, right? Because A0 is X10 and so on, right? Because we're using the application binary names here in this particular example. And ultimately, we end up in a loop where we go through one byte at a time until we're done. All right, now let's throw this away. We're not even going to run it. Let's look at the exact same code written with the pseudo instructions, okay? This is going to be a little easier to read, okay? And it's shorter, too. This should be a little bit more pleasing to be able to look at and debug and understand, right? I wanted you to see both, because when we try to disassemble this and look what we're dealing with, we're going to see 2 instructions for every one of these pseudo ops, right? We already talked about that. I wanted you to see a kind of a side-by-side end-to-end comparison here of what it looks like longhand versus shorthand. And those percent PC rel high and percent PC rel low things, those are the functions in the assembler that allow you to figure out which is the 20 bits belongs in the LUI or the LAPC part versus the add immediate, all right? None of that we have to worry about if we use the pseudo ops, all right? So we don't need to get so much into the detail there. We just need to understand that there's a little bit going on under the hood when we use these pseudo ops. That's the whole point of that, right? Now, what's going on with this thing? Well, if you look at the documentation for RISC-V, in how to start up a C program and build up its address space and the ABI rules and all that, this GP register, which is what we refer to as the global pointer, okay, and is the ABI name for register number X3, and I should probably put a comment over there. GP equals X3, right? A0 equals X10, which equals this, right? And A1 equals X11, and so on. A2, I'll go ahead and add a comment for that as well, equals X12. Okay, what are we doing here? We are getting ready to zero out the BSS, right? Because no one's doing that for us. So what do we need to do? We need to get the BSS start address in some register and the ending address in a register and put 0 in a register so that we can use this like A2 register down here. We're going to use it to store, as you can see, the 0 into the array one byte at a time. So what happens is, it turns out A1 is actually the end of the zeroing plus 1, right? So BSS end, in other words, is a label that represents the first address past the end of the BSS, right? Or BSS start is a label on the first byte at the beginning of the BSS. So this should make some sense here. What do we got here? If A0 is greater than or equal to, in an unsigned comparison, the contents of A1, then go here to done BSS, which is down here, and we e-break right away. Okay, we're going to take it one step at a time. Just zero the BSS out and see if that works. All right, we can't do 90 things at once. Nothing will work. We won't know where to start debugging. One thing at a time. Okay, so what's going to happen here? We're going to say when first time through, if BSS start is, say 1,000 in hex and BSS end, let's say is 2,000 in hex, just to have some example there. Well, then 1,000 in hex is not going to be greater than or equal to unsigned the contents of the 2,000 in here, right? It'll be less than that. So what's it going to do? It's going to say, well, store the contents 1 byte. All right, from the contents of A2 into 0 off of A1. So this is 1 byte at a time. I'm going to store it into memory at address in A0, I should say. Then we're going to add 1 to A0 and put the sum into A0. Then we're going to branch. We want an unconditional branch back to the top of the loop and keep going. Yes, I could optimize this, but right now this is meant for readability, not optimization, okay? So what do we got here? Branch if equal. If the contents of X0 is equal to the contents of X0, and by definition it must be, it also happens to be the value of 0. But if these two things are equal, go to clear BSS. There is no unconditional branch in RISC-V. You do it like this. You just compare any register to itself and say if those are equal, go to where you want to go. All right, so it goes back up top of our loop. A0 will have been advanced. This will obviously go through until A0 advances itself all the way up into the point where it equals A1, and then it will stop. Okay, and A1, of course, is when you're not supposed to be zeroing out anymore. So this loop is doing exactly what we would want it to do. And then it will immediately stop. Okay, so let's go ahead and run this. Now I provide you a make file. Let's take a quick look at what's going on here. In my home directory on Hopper, there's this path here. If I type pwd, it gives you the full path: home, Hopper, Winans, yada yada yada. The tilde here is shorthand for my home directory. Okay, and in this directory we see these files right here. Oops. And there's a bunch of make files and everything else. All right, so these are all set up. You can make a copy of this directory anywhere you want. Like, for example, if I want to, I can just say copy recursively the directory that we were just looking at to whatever I want to call it, okay? XXX. And this will make a complete copy of every file in there in my, my target place, and I'm going to call it XXX. If I can type, all right, we can see all the files sitting right here. So this is my own personal copy of this versus the source, right? So I can make another, you can make a copy is my point. We can test the whole thing by typing actually make clean to walk through the entire tree and test the make files that they all work. They've been moved, make sure all the path names and stuff work out okay, right? So we were looking at standalone number 1, and we wanted to compile it up, and we want to run it. So again, we see the compilation looking just like we did before when we were doing the assembler, especially for CRT0.S, okay? We come along, and what do we got going on here now? When we compile here, I have this thing called load script, and this is new from the last build. Now, what I'm giving you now is a special script when the link editor runs that has some specialized commands in it that are handy for this particular simulator that we're using. I've also said, regardless of where you want to put it, just put the data region, start the data region at hex address 10000 like this, so that I can find it more easily and I can recognize what I'm doing, okay? Now, when the thing runs, what did we end up with? We ended up with a program and some other stuff. So the first thing we can do is we can type nm on the executable if we want to, and we can sort it, or you can actually type nm-n, and it will actually sort it itself without having to pipe it into sort like I showed you last time. Either way, it'll work. So what do we got? We got the start. We can see these labels: start BSS, clear BSS, and then we see these down here that are provided by the compiler, including this global pointer address. Again, all this stuff is created for us when the thing is link edited and we create the executable. And remember, we then ask with obj copy to extract out just the binary part and put it in this bin file here. So you can see we have a 48 byte file that contains the contents of this part of the code. All right. What do we know about this? We know that the data begin, the BSS start, BSS end, all the, look at every one of these has the same address. And we saw this before. Every one of these at the same address means there are nothing is in the BSS region. There's nothing in the data region or anything like that, okay? So what's this program going to do? It has nothing to zero out. Well, that's certainly one of the cases that we have to handle, so let's make sure that works. Now, in this make file, again, on Hopper or Turing, you can just type make run, and it'll run the version of the simulator that I'm giving you. It's my binary. It's sitting right here in my home directory /463. So it's RV32i, RV32i, and I wanted this particular make file. I want a M40. I want 40 bytes in hex of memory. I want to use these options, and I want to execute prog.bin. So we have a pre-simulation, disassembly of all the instructions in here, and you would expect to see these pairs. Remember, we used LA for all these things, so these are all the pairings. This here is where we put 0 into A2, which is the ABI name for X12, right? And here's our little loop. Branch if greater than or equal to unsigned. If X10 is greater than or equal to X11, we're done. And it would say, oh, if that was the case, go to 2C in hex, which is down here at the E break. So this matches very nicely, as it should, the crt0.s file, right? We're assembling everything, so that includes junk data at the end because it went all the way down to 40 bytes, right? We can watch the execution trace here if we want to, but what's going to happen is it'll eventually get to the point where it starts the loop, right? Which is where it's this BGEU right here at address 1C. So we can watch the program counter wander off to 1C. What'll happen is the first time it gets in here and it wants to compare these two registers, they're both going to be set to 1000, right? And therefore, what'll happen is if it's greater than that, it will go to address 10. Rather, it'll add 10 to the program counter, I should say. Otherwise, it'll add 4. So it goes from 1C, it goes up to 2C, which is where the E break is, okay? And it immediately halts. We can come down here, and here's our memory. I mean, it didn't do anything, so gall darn it, it didn't break anything either. That's very nice, so that's what we should expect it to do. And all that for nothing. So one last look at the crt0.s. When it is used to not set any BSS data at all, we verified that it did indeed skip over and stop without trying to, set a bunch of memory that's not supposed to. Now, I kind of glossed over this global pointer thing. It turns out that the way we're running our simulator, because we say no relax, the global pointer is not going to get used. Because in order to use it, we have to remove this no relax thing that I have coded in there, all right? Now, the reason the no relax is in there, and the reason you see it in here as well, is we're telling the assembler, and more accurately, the link editor, not to try to optimize our code in here. I think I talked about that before. It's important that we don't do that right now because it makes it difficult for us to match the optimized code to our source code in here. And that, we don't really care about performance right now as much as we care about understanding. Okay, so I'll leave that on. It turns out it won't get used, but it's in here for sake of completeness because the global pointer will be used if you ever remove the no relax instructions and let the code get optimized. Like when you're running the C compiler on the C code, you might decide to, let's try to optimize this and make it run with less instructions or something like that. And if you do that and you forget to then add this to the crt0.s file, then the thing won't work. So this is in here only for sake of completeness, all right? The minimum set of startup is what you're looking at right here. Set the global pointer register, zero out the BSS, then go off and do something, and when you're done, you e-break. So let's go now to stand number 2 and see what that one's all about. we still just have an assembly language program. Well, let's look at this thing. Well, there's a lot going on in there. We better open it up with the editor so we can see what's happening. Starts out the same. Now, again, this is the boilerplate stuff that you put at the beginning of an assembly language program. This simply says put the instructions in the text region, okay? This thing has to do with the link editor file and stuff like that. This says I want a global symbol called start. I talked about this before. This down here tells the debugging information in the ELF file that we're not really going to use. That start underscore start here, this label is actually that of a function rather than like a variable or something like that, okay? We come down here, we clear out the BSS, nothing new, nothing new, nothing new, nothing new. We fall to the bottom, we e-break. So far, so good. This size thing also has to do with debugging data along with the function stuff. So you can see this in a lot of assembly language programs. I throw it in here so that you're just familiar with it if it pops up in the future. It really means nothing in the application that we're messing around with here because we're not using the debugging information in the load module, okay? So like the dot text above, we put a dot data down here. It says, hey, I want to put this stuff in the data region. So what's the difference now? The difference is I'm going to have stuff in the data region this time. And what's it going to have? It's going to have 4 words with these values, 1, 1, 2, 2, 3, 4, 4, which is an assembler, very much the same thing as if you had a C program and you said int32 and you created an array and you initialized it like this to 4 initializers in here. You'd end up with the same kind of thing. So this is the assembler version of a global variable in a C program that looks like this, all right? And here's another one that we just did for the sake of it. 4 more with longer names, okay? We call this one V1 and that one V2 on these for the address where these things start, okay? Now, if I want to put something into the BSS region from an assembly language program, I got to use a very different approach. This kind of goes way back to like Fortran and stuff like that in the common section, all right? So the BSS is kind of like a Fortran common section. So the way this works is that we say in the common section, create something with a symbol called B1 that uses 4 bytes of data. So that would be in a C program a lot like having a global variable defined like that. Down here we say in the common region, create a variable and a symbol for it called B2 and allocate 16 bytes for this one. Now that would be a lot like in a C program creating an array like this. Okay, so let's go ahead and compile this one up and have a look, see at what's going on. Okay, I could type make world, which causes it to clean and recompile everything so that in case it was already compiled, it would start over again. Okay. Again, you've seen this a gazillion times by now. Could create this thing, and then we say, okay, let's go ahead and run it through the link editor. And again, this is some extra stuff beyond the basic freestanding stuff that we talked about before. So we can force that starting data region to go at a known address so it's easier to find. And again, we created a listing in the binary and so on. So let's go ahead and look here at this listing file. What comes as no shock that this looks like the other one does, right? Because why? It didn't really change. We didn't change any of our code at all, okay? And when you have an assembly language listing, it doesn't list the data in the BSS and stuff like that. Now, there are options for doing such things, but that's not really our number one, not the most important thing right now. Let's look at the names of the program file, the executable, the load module that we have that still has all the symbols in it, all right? So what do we got? And here's the start and the clear and the done BSS. These lowercase letters in here mean these are not global variables. These are just labels that are in that code that are available for us for debugging reasons, but they're not able to be accessed by any other file, okay? So that's what lowercase letters mean in here. You can always type man and M on a Unix or Linux system. It'll tell you what all these letters mean if you want to know. The capital ones are global and the lowercase ones are local, all right? The T's are the text region. The big D's are the data region. The B and the B's are, they should be the BSS, but these are local because I did not declare them as global like I did, when I created the start label and so on. But it doesn't really matter because all this is contained within one file anyway. The key to this example is that the BSS start the BSSN have different addresses now. So this lets us test our loop out to make sure the thing is zeroing things out correctly. So again, I can type make run, because in this make file, there's a target that will allow us to run this executable. Now I asked for a whole lot more memory, and things are scrolling crazy here. So let's go ahead and run it and pipe it into less. So I can hit space and I can walk through this. Now this is going to run for a while because it has to go through that loop many, many times. Here's the store byte, right? We're storing zeros into these various addresses while we're zeroing out the BSS. So we'll see a store byte. Here's the one that goes into 1032. When the next time we come around to address 20, it'll store another byte in the next address. So 1033 and so on. Now you can go like this until it's done and it looks like we're done here. Or what you can do is you can do a text search for the word terminated, and that's what I do quite often. So let's go back to the top of the file in less. I'll show you how to do that. Tell me 1G takes you to line number 1. If I type / terminated, what happens is it'll search for the word terminated in the file. And that'll take me right down to where the program execution obviously ends. And if I hit K or up arrow or something like that, I'll scroll up. And I can see what it did right before it terminated. And I can see it doing its BGEU, and I can see the E break at address 2C. And I remember that these are the addresses. This is the E break at the end of the CRT0.S. So I know it ended the way it's supposed to. It didn't like run off to some illegal instruction and die, right? So it terminated by an E break. The only one on the whole program is the one that it's supposed to execute when it's all over. Okay. So, what do we got now? Look at the memory in here. There's a lot of zeros right here. Were there that many zeros? No, there weren't. Oops, I went too far. We can back it up a little bit. Remember the 1 1 2 2 3 3 4 4 and the 1 1 1 1 and all this stuff. We remember all this, right? Those were in the data region, right? What comes after the data region is the BSS. This is the BSS that we zeroed out, okay? Now, where did all these other zeros up here come from, right? Well, let's look and see what that's all about. If we look at the prog bin, look at how big it is right now. Hex dump -C, prog bin, let's put this into less because there's going to be a lot of it in here. Oh, it suppressed all the redundant lines. So in prog bin, remember when I link edited this, I said put the text at 0 and start the data region at 1000. Well, it has no real option other than to say, well, here's the text, and that's the end of the text. The only way to get the data to start at 1000 is to simply fill the file, the binary file, with padding. So all the zeros from address 30 all the way up to FFF is just padding to fill out the text region so that it ends where the data region is supposed to start, okay? So that's what all those extra zeros were when we did the run. Okay, I'm going to hit capital G and go to the end of the file. Now I'm hitting B to go backwards one page at a time. Is another way to get to the end of things and look at it backwards if you want. So if you're going to print it all out in detail, that's where all these zeros come from. This is the padding in the text region, okay? And we'll notice that the data region starts at this address here. Again, we can go nm-n prog because we might have forgotten all these addresses, right? Well, the BSS starts at 1020, and the BSS ends at 1038, or the byte before that, right? So if we scroll up to where that happened, 1020 to 1037, there's 1038, which is one past the end of the BSS. So this is a perfect test of both empty BSS and a BSS that has some data in it, right? So in other words, this program works fine as well. It does what it's supposed to. And we're in standalone test number 2. Let's move on to standalone test number 3, okay? I say standalone. Some systems call freestanding programs standalone programs. And I tend to go back and forth. I'm sorry. Too much history there. So what is this one going to do? Well, look, we have a C program down here. We're finally going to get to the point where we're going to call a C program. All right, so we see that this crt0.s file starts out exactly the same as everything else that we've looked at so far, right? And it uses these nice pseudo ops so we can see what's going on. Now, when the BSS is finished being zeroed out, let's see what's happening down here. Now, we're using the ABI names, right? So A0, A1, A2. The A stands for argument, right? These are the argument registers. So we can set them. These are supposed to be the 3 arguments that we're going to pass to main. Okay? Now, what are the 3 arguments that main can take? Well, you have the arg-C and the arg-V, right? Well, I'm going to just say there's no arguments at all. Okay? Arg-C is 0. Okay? And then arg-V, well, you shouldn't be poking around in there if you don't have any arguments, so I'm going to just set that to null. Now, there's another one called ENVP that a lot of people leave out. This is not actually part of the official standard. However, it's incredibly widely supported. The vast majority of all Unix systems support this 3rd argument that has to do with environment variables, all right? So it's kind of important that we make sure we cover it. Now, we're the people writing the main routine, and we're not going to use it. But I throw it in here because if you look around, you will see this in some other programs, all right? Now, whether they're set to null or not is another story, but the bottom line is that main in the new lib on running on a Unix-like system will have 3 arguments quite often, okay? And that's what they're for. Now, there's a pseudo-op called call that we'll introduce here to make it easier than writing it out longhand like this. Now, remember that jailer is an IML, rather a type I instruction. Just like add immediate, right? If you go down here into rvalp and you look down here, you see jailer is an I-type instruction. And you've got a destination register and you've got an immediate value off a base register, RS1, which is very much like any other I-type instruction. You have an RD, you have an RS1, and you have an immediate. And the way all these, like add immediate, says add immediate to RS1 and store it in RD. Now, the way you write this is a little bit different, but it's doing the same thing. Add this immediate value to the contents of RS1, okay? Now, jailer is going to go to this address because it's a form of, it's a jump instruction, like a branch instruction. And it'll set RD to the address of the following instruction because that's what jailer does, all right? Now, we need to remember that IMM here is sign extended, right? So the immediate operand is put down here, least significant bits, and the sign bit is extended. So we still have this game that we have to play with these special functions and stuff in the assembler to make sure that we got to remember to add 1 to this value here if this low 3 hex digits looks like it could have be a negative immediate value, all right? Again, this is just like the LI and the LA in that respect. Now you can see I got a pound if 1, and this is effectively commented out. So call main is a whole lot easier to understand and read than all this malarkey down here, okay? But again, when you use this pseudo op, you're going to see, if we look at the disassembly, that it'll turn into these 2 instructions down here. There's the only reason I wanted you to see all this. So we clear out the BSS, we set the global pointer, we make sure that we got our argument set in a reasonable way that we're not even going to use in this example anyway, and then we're going to call the main function. And this pseudo op is implemented to follow the ABI rules, and it will use the X1 register for the return address when the jailer is generated, the jailer instruction in here, because it's following the ABI rules, okay? So when main is done, what does it do? It's going to return. What does it mean to return? Now, the ABI rule says that X1 will contain the address to go to when the subroutine returns, okay? If you're familiar with a mainframe assembler, jailer is like bailer, okay? And then it sets a register that says, hey, when you're done, go here. And it'll set X1 equal to the address of the next instruction, which is going to be this E-break, all right? So when main is done, it'll come down here to this E-break, and it will halt. So if we compile this program, we can see that we compiled a CRT0, like we've been doing all along. And we also compiled a main.c file. Then we run the link editor like we've been doing all along, but we put both the CRT0 and the main.0 in here. We need to put CRT0 first, so it comes first in the file, all right? Because remember, our simulator starts up by just branching to and executing instructions starting at 0. We really need to make sure that the CRT0 comes first. If you put main first, it's just going to start executing the main code, and it will not have zeroed out the BSS or anything else, okay? It would be very confusing and probably die pretty quickly. All right, so let's go ahead and look at the listing that it created, okay, from that source, right? Again, we see these pairs, right? These are the expanded pseudo operations. So we see the start to the clear BSS. We've looked at that enough times. We know what's going on now. Now, when the BSS is finished, here's those 3 instructions. X10 is A0, X11 is A1, and X12 is your A2. Remember, we put 0 in X1 here. That's because the high address that we need is 0. Main is only at 44 over here. So there's really nothing to put in there. So we always PC, we add 0 to the program counter. And then when we do the jailer, now remember, when we add 0 to the program counter was 38 right here. So 38 plus 12 in decimal equals 44 in hex, right? And it helps you over here. This particular disassembler reminds you that, you know, this thing here represents where the symbol main is at address 44. So that's one of the benefits of generating this nice listing for us. So it's going to jailer over to there and leave X1 pointing at the return address. So what happens in main? We didn't even look at main yet. Well, we can look at this over here and see what's going on. What does main do? It does a Louis on X10. It put 8675 in hex into X10. And then it adds, what, a decimal 777 to X10 and stores that in X10. Well, it's kind of unfortunate that we're mixing decimal and hex, but it does this handy-dandy favor of telling you, by the way, that the sum of all this with this over here is going to put the value 8675309 into X10. Now, according to the ABI rules, remember that X10 is also not just the register of the first argument. It is the register that holds the return value when the function's done. If it returns an integer, it'll be in X10. So that's what it's done. The main routine, if we look at main.c, we'll see it does nothing more than returns that number. Pow, done. Okay? And because of that, it can be optimized down to just put that in the register that holds a return address, and then jailer to 0 off of X1. And the fact that there's a 0 over here, remember how the jailer works, is it says, well, if the destination register is 0, then don't bother to save any return address. So this is an unconditional branch to X1. That's what this is. There isn't an instruction that does that, but you can easily do it with jailer. 0 off of X1 is branching to X1 and saying throw away the byproduct of saving the return address. If I were to call a subroutine with this instruction, we're going to just simply go back to wherever X1 points, which is going to take us back here to 40, okay? And when we get to 40, we'll have returned our return value in X10. So if I say make run, pipe this into less because there's going to be a lot going on in here or something. Oh, it ends right there. Okay, that's not too bad at all. What happened here? We came down here. The last few things in main were to do this, right? And we can kind of verify that that is what happened. X10 is 8675309. And then we see main saying jailer to 0 off of X1, and it just simply says, okay, well, it wants to store the return address in X0, which it's going to throw away, and the PC equals 0. Okay, that's your immediate offset right there, plus the contents of X1, which is 40. Okay, and remember that in RV32I, it needs to make sure that the least significant bit is a 0. So that's why it's ANDed with this value over here. And we ultimately get 40, which is where the E-brake is, and it halts. Okay, no big deal. And we can see when it halts, register 8, register 9, register 10 right here has the value in it that main tried to return and did so successfully, right? And here is the executable module that has all this. Now, this is all going to be full of A5s. Let's look at the bin file. It's going to be really small. Why is this one small? The other ones were big. That's because we have nothing at all in the BSS or the data region. All right? This program didn't put anything in there. So there's no reason to have anything at all. We just need to have the instructions as far out as to the end of main, which would be just a little bit beyond this hex 44 here. So that makes sense that we would have 80 in decimal bytes or thereabouts, right? We can have a look-see. Oops, that's not what we want to look at. We want to look at this guy. Okay, and that's all she wrote. Up through 4F. Not a problem. So if we type make run again, we should see the memory filled through 4F, which we do right here, and we see nothing touched anything down here. Okay? I'm sure we never even used the stack. We called a subroutine without even using the stack. Well, why? Well, there was no reason to save anything. Remember on the RISC-V, when you call a subroutine, you're going to have up to 8 arguments stored in the registers X10, 11, 12, 13, 14, and so on. That's why they're called A0, A1, A2, and so on. And remember, you can look up all the meanings of each one of the register, the role-based names over here in this column, along with their physical names over here in this column, all right? So A0, which is X10, is where it says this is a function argument, and when a function returns, it's the return value. Notice there's an extra return value over here. That's so that if a function has to return a 64-bit value, it can put half of it in each one of these 2 registers, okay? Now, it goes on up to the 8th register here. If you have more than 8 arguments to a function, which is not very common, you would push the extra ones onto the stack before you call the subroutine, right? So because we didn't do that, we don't need to use the stack at all. We've got the arguments to our function that we're going to call main. We put them in A0, 1, and 2 in this particular example. We store the return address, which could be also called RA. We put that into the register X1. And since main never called another subroutine, it had no need to actually save this, because obviously if it called another subroutine, it would reuse X1. It would also reuse these arguments here if it needed to, right? So it might need to save all those if it made another subroutine call. Where would it save them? It would put it in the stack, okay? But since it never made another subroutine call, we were able to go into main and back out without ever touching the stack at all, okay? That makes this faster than machines that have to store all of its arguments to the subroutines in memory somewhere, okay, like putting them in the stack or building a table of pointers and things like that. This machine runs pretty quick because all it ever needs to do when it's running code like this, and all it needs to ever access are its registers, it can just simply fetch instructions and execute them. It doesn't have to go to memory back and forth constantly to get other things, which causes all kinds of slowing down and contention if there's more than one CPU in this system, right? It's nice not to be using the memory all the time, okay? So we're going to minimize that, and we can get a higher throughput overall. So let's see what the next example looks like. All right, so we got our CRT0 again. We got our main.c. We go through here. We see this is exactly the same as the last one. I remove the extra comments in here that shows you what the call does, all right? So we haven't changed CRT0.o or CRT0.s, I should say. What do we do to main.c? Okay, so main.c, this time it's got some global variables in here. Now, this is a lot like that second version where we had the BSS and the data region in here defined, right? When we did it in assembler. Now we're doing that in C. We're much more familiar with this. So what do we know? We didn't give these things any initialization values. Therefore, according to the C language, they'll be initialized all to 0. Okay, and that is why we stick them in the BSS. Okay, so these are going to be put in the BSS. So what do we got here? We got 1, and we then got 4 more. So there's 16 bytes here plus 4 bytes there that all will be sitting in the BSS. When this thing runs, it's going to set this value, and it's going to store it in the last element of this B2 array. Then main will return a 0. Okay, so let's see this one run. Okay. Again, the compilation is the same thing, freestanding and the usual flags here. Down here, when we do the linker, we use the same everything here. Put the data at hex 1000, put the text at 0, no change, no change, no change. Okay, let's now look at the program.list file. No change up here. It'll eventually get down here to main. Look what's happening in main. Main has to actually do some real work now. So you see it doing a couple of things. It's going to put what it did, a Louis of 1 into X14, which is really going to store 1 with 3 zeros after it, okay? Which coincidentally is the starting address of the BSS. Minus N prog. We can look in here and surprise, surprise. So that is where the BSS starts. So certainly the B2 variable, and the B1 starts at 1010 in hex. So we'll see that get used for accessing the elements in that array. So this is setting our X14 to 1000, and we've seen these two before. This is how you can put 8675309 into, in this case, X15. We see then store word X15 to 12 in decimal off of X14, which is going to write it into address 100C. Now I'm a little bit confused because isn't that the fourth full word into the BSS, right? So why does it call it the data begin and so on? Well, it's because the object dump routine that printed this out doesn't know which label is what, okay? So it just picks one of them that is the closest one to this address. And it says, well, relative to this address plus C is what we're dealing with here. So let's take another quick look at the executable load module and all the symbols in here, right? So why did it pick data begin? Well, it's probably because it was the first one it found and that all have this address, okay? It could have just as easily used any of these. It would have been nice if it told us it was BSS start plus whatever, but because every one of these has the exact same value, it has no way of knowing which one we really intend to use, okay? So that makes sense. And it just picked the first one it found. No problem. Now look closely. The B2 variable comes before the B1 variable. All right? Now remember, when we wrote main, I put B1 and then I put B2. Why did it reverse these? Okay? Well, the compiler can do pretty much anything it wants. In this particular case, I believe the reason it put B2 before it did B1 is I think it sorts all of these global variables based on their size. And it puts the biggest ones first and the smallest ones at the end. I believe it's as simple as that. You'd have to read the notes on the compiler. There's probably some options and arguments that you can give the compiler that tells it not to reorder them, or you could change the rules on how it does all this stuff. But I think by default, it just puts the biggest ones first, and obviously B2 is the biggest one. All right, now that is why when we look at this program down here, it's storing the value that's in X15 in a memory at 12 off of X14, which is the address of where the fourth element in that array starts, okay? at this address right here. When it's done with that, what does it do? It puts 0 into x10. Well, that makes sense because remember, x10 is the value that, or the register that's supposed to hold the return value for the function. And main.c, as you recall, had a return 0 in it. It then branches to x1 and throws away the return address. When this gets to here, it's returning from the jailer up here to execute the e-break right there. So let's go ahead and run this now and see what happens. All right, the usual stuff. It's going to happen. You see these BGEU. It's going around and around and around, probably zeroing out the BSS right here on its merry way. As you see the 100B, the 100C, the 100D, and there'll be an E and an F right here. And then I believe it'll have to do 4 more in there. For the other variable, it'll end at 1013. And at that point, it will branch out of the loop. And remember, that's this BGEU, because when 14 equals 14, it has gotten to the end, right? That's the address of the end of the BSS, at which point in time it's going to set up the 3 arguments that it needs to call main that we ultimately don't use, but that's what's happening in there. And then what's it doing? It's going to OWPC and jailer. This is the call operation that we use to call main. Okay. And then when main starts running, there's that Louis 14.1 we saw, which puts the 1000 in hex into 14 right there. And it's putting the first half of this value that it wants to store in the array into x15, and then it puts the 309 in there, and there's the store word where it puts the value into the array at address 100C. Okay, stores the value of x15. Puts 0 into the register that holds the return address, goes back to where it came from, and then it does the e-break. Now we scroll through the memory. Here's where it loaded the text. Now remember, the text had no data region this time. So there's nothing to there's no reason, I should say, to pad out the text region until we get to the data. So it didn't, all right? So this is a small little executable. Then we get down to where the BSS was zeroed out, which is right here. When the program ran, it stored 8675309 into the 4th element of the array called B2 that starts at this address right here. So that's what happens here. It works perfectly. The other variable was never changed, so it was set here. This is where B1 is, right? At 1010, right? So if we rerun the nm command on the load module to remind ourselves exactly that that isn't the case where those variables were. All right, so perfect. So far, so good. We're running our nice little C program here. So why are there more examples? Well, there is a little bit more work to do ultimately. What's going to happen in here? This one is going to have data and BSS, and we're going to set multiple values in the data and the variables in the BSS. So the B2 is a variable in the BSS, and D3 is something in the data region. And then what do we got here? D2 is also going to be in the data region. So this is really the same test we just did before, but this has more than just BSS, and it has some data because they're initialized in here as well as the BSS. So when we run this one, we'll see that it had to pad out the probe bin here, quite a bit in fact, to get the data out to where it needs to go. How big are these arrays? They're probably, oh yeah, these are pretty big arrays, okay? That's why there's so much data out there. So let's go ahead and see what's happening here. We clear it out. The CRT0 is the same as the last one. It calls the main. The main's going to play around with values that are in D3 and D2 in the data. Now you see these addresses going up pretty quick here because these are pretty big arrays, right? There's a lot of stuff going on in there. Then there's the what do we got here? The This is the D1. So this is a variable that just has a single value. These are arrays, and this is just a single variable. So you can see that this is the small data region, and these are the big data regions here, right? After the data is done, we have the BSS, and they're not particularly big. We end up with a couple of 16-byte arrays like we did before in the BSS. So if we type make run, and I always pipe it into less because less lets me scroll this around. And now this time I'm going to search for the word terminate like I talked about last time. So we can skip the executing of the program. We know what it's supposed to do. The program runs, and when it's done, it will have stored some values into some of the arrays. All right, again, this is the padding that it has to put in there into the text region so that the data region can have initializers as well, and we see this stuff down here. So those are the initial values in one of the arrays down here, right? And the other array is probably down here a little bit. The data arrays actually were very large, so we'll probably see a lot of zeros here, because remember, if you don't initialize an element in an array, it puts all zeros in here. So this is probably where the second array starts, and there's some stuff in there at 1FA0. And we go along, we'll probably see the BSS down here. And that is probably where another variable is at 2F5. So we look down here. What do we got? We got 2F5, 4, 2F5, 8. So we've got these two BSS guys here. And what are we doing here? We're looking at B2 sub 3. We're looking at D3 sub 0 and D2 sub 0. You run all these things out and calculate the addresses by hand of where these are. Well, obviously the 0th elements are at the beginnings of those arrays, right? So, and by the way, if I ever say exclamation and then a thing like this, this is a bang, bang NM. It just says rerun the same command that I ran most recently that starts with NM, which was this, okay? So I can easily rerun that without having typed the whole thing in again. So what do we got here? We got D3 is going to be where? At address 1000, and it should have this in it. D2 should count in the opposite order, okay? And it is D2 at this guy right here, and B2, the BSS, is going to have this phone number from Tommy Two Tone's song at B2 sub 3, which would be the last element of this 4-element array here at 2F44, which will actually store it at 2F50. So if we type make run again, we go to the end of the file, and we look at, well, actually, it's probably right there. 2F50 is where it actually stored it in little endian order, 8675309. And then what was the other one? We stored something in D2 sub 0, which should be at 1FA0. And we did D3. So at 1000 and 1FA0 should both also have those values in there. So at 1FA0, that's exactly what we got. Blah, 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 right there. And then remember, what we're doing is storing over an element in an array that was initialized to 1, 2, 3, 4, 5, 6, 7, 8, and so on. 9, and then hex A is at 10. So that makes perfect sense. And the other one is at 1000 in hex, which we see right here. And I write over that 1, 2, it's going to be 1, 2, 3, 4, 5, 6, 7, 8 in hex because it's little endian. And remember, this was 10, 9, 8, 7, 6, 5, 4, 3, 2, 1 in its initializer. So if we cat out main.c again, that's exactly what we saw. 1 through 10, 10 through 1. And everything here makes perfect sense. This is really not a lot more than we saw in stand 4, but this is both a BSS and data at the same time. Let's look at stand 6. So what's so great about stand 6? Main.c, what's going on in here? We got hello world and return 0. We've got some things in the BSS over here. Okay, let's see what's going to go on here. it compiles. Let's make sure there's no funny business going on in the CRT0 file. This is the same one that we saw last time. Okay. Let's not run it just yet. Let's have a look-see at what's in program.list. The usual stuff for the BSS. Then we get to main. Well, that's interesting. All main does is put 0 in x10 and return. That's all it does. Well, we were just looking at main, and it has this array over here that gets set to hello world. I would expect to see something going on for that, right? I mean, yet we don't. So the purpose of showing you this example is to show you that the compiler is optimizing things, all right? I've created a variable that no one uses. It's a tree that falls in the forest and no one's around to hear it. Should the compiler actually create this, initialize it, and then throw it away if it knows that nothing could possibly come of that? No. So it didn't even bother doing it, which is really strange, right? But it makes sense. It optimized it away. What it should have done is allocated 100 bytes on the stack and then copied in these characters to initialize it, okay? Let's go ahead. We can say make run. Oops, if I can type correctly. And this program will work, but it won't have created an array nor filled it in because we just looked at the code in the main. In fact, it's right here. It's put 0 in x10 in return. Okay, so it never created an array. It never filled it in with hello world. This is a tiny little program because the text ends here, right? There is no data. There is no BSS because if there was, we wouldn't see all these A5s in here. We would have padded it out with zeros. What it did do is it zeroed out a bunch of stuff here at 1000 at 1010. And the reason it did that is because it does have these global variables over here, right? And if we look in here, we can see them. There's the main that doesn't do anything. And then here we are in the BSS with these two variables, B2 and B1. Again, it sorted it so the biggest one comes first. All right. So this is a kind of an anticlimactic thing, but it's a little wake-up call to make sure that we're always aware of the fact that the compiler might actually remove something. So we need to make sure that that we understand what's happening. Okay. So now what's going on? What's going to happen in this version here? Let's look at CRT0 rather. Let's do a view on that. Okay, so what's going on in here? Nothing interesting at all. This is the same one that we've seen for the last 4 or 5 examples. What's main.c doing here? Well, we now have a myfunc.h. We can pound in standard int.h. We have the same BSS variables that we have before. We have this array here that is, 100 elements, but I fill in 1, 2, 3, and I call myfunc, and I pass myfunc the address of that array. Now the compiler has no choice whatsoever. It has an array, and it's passing the address to a function. It has to create that array. It has to initialize the array because the compiler, when it's building main, has absolutely no idea what myfunc is going to do. Okay, what does myfunc actually do? Well, myfunc, right down here, is going to take this. What's it going to do? It's going to add them all up until it hits a 0. Okay, so it's going to add 1 plus 2 plus 3, and then it's going to get a 0 because it's going to have 100 characters total. And after the last one in here, it'll put all zeros, right? It'll pad it out with zeros to make it the full array be initialized. Okay. All right. So this is then going to go through all those characters one at a time. It will just add up 1, 2, and 3. It'll reach the 0. It'll come out of here and return the I. So let's go ahead and compile this. And what happens? We have an error. Now, this was on purpose. It's supposed to have an error. Why does it have an error? Who in the heck called memset? If we type grep memset on star.c, absolutely no one called it. How in the world is that getting done, right? Well, this is where you have to understand your compiler. This compiler and pretty much all compilers, comes with a set of libraries and a set of rules that says, look, there's no reason for me to have to generate all the code to implement the initialization of that array, okay, when I can just call a standard library routine like memset. So if you're going to use the GNU compiler, you have to be careful. It may call any one of a number of standard library functions. It also could call any one of like 100 other special functions that are custom to the compiler. Now, we've just seen what that is all about. Let me clean this up because this is a broken build. Again, this demonstrates the next thing that we need to deal with, all right? So what does it really mean? Well, it means when we do the link editing down here, we have to say, I want you to put in my CRT0 and my main.o and my myfunc, but I also need you, when necessary, to go and get some more stuff from some libraries, okay? And what are those libraries? This thing comes from the standard C library, and all these other functions I mentioned earlier, like 100 plus of them, come from a special custom compiler library. So where are we? We're in stand 7. Let's look at stand 8 and look at the differences in here. So I'm not going to see any difference in main. I'm not going to see any difference in here. Okay, these are all the same. What is different? Is there something special about CRT0? No, there's not. This is the same as well. All right, we can do diffs and you can see are all the same. Feel free to do that with your own copy of these files. The difference is in this make file here. Watch what happens if I type make now. See this right here? This is the only difference between the build in stand 8 versus the build in stand 7. What I'm doing is I'm saying build all this stuff out of my files. If you need more stuff because there's functions that need to be called that aren't in here, try looking in something called libc. If you can't find it in there, look in something called libgcc. Okay? Now I'll leave it as a task for the viewer to go romping through these things and see what's in there. I'll show you how to find them from this compiler. That's not too bad. It's a fairly straightforward thing. You can execute these commands that come with the compiler. So because the compiler is being run with a full path name like this, I got to copy and paste that, right? You can say at any time, where is my libc.a, all right? When you say -lc, what that means to the compiler is to go find a file called lib followed by c.a, okay? Now I'm going to ask the compiler, where the heck is that file? Where did you find it? Okay. Now it turns out it's part of the files that are all installed when I built the compiler on this machine. And when I built it and I said install it, I said put it here. Home Research RISC-V32/install. And inside here, it's got gazillions of files, one of which is this libc file. Now, you can use nm on a libc. Oops, there was a missing slash there. Hang on a second. You can use the nm command on a library file just like you can a .o file, okay? Let's pipe this into less because there's going to be a lot of stuff that comes out of here, right? Now, this is a little bit different than just one single .o. This is a library, which is kind of like a zip file. It's got a whole bunch of .os in one big file. So what it's going to do is it's going to come through for each .o and say, here's all the labels in there. Okay, here's the labels that are in this file. So any time I call a command, like for example, memset should be in here. So I should see, now memset is called by a lot of things. Let's look and see what, let's find one of these that's recognizable. calloc r b0. All right, so b0 is a function, a very old function that's been replaced by memset. So you're not supposed to use b0 anymore. You're supposed to use memset. So the way this is, it suggests, is b0 is a label in the text section, okay? And when this function runs, it needs something called memset, and the U over here means it's undefined. So what's happening here is I can see that if we go find the source code for B0, it probably just has one line of code in it that just says call memset with the appropriate parameters. But the memset has a U over here which says this calls memset, but it's not supplied by B0. It's in its own file somewhere else. It's also called by a bunch of other things. Okay, I don't even know what this one is. Look at all the stuff that this is using, all right? This is find FP. I don't even know what that means. Probably some floating point thing. I don't know. If we go along in here, we'll eventually find memset. Those are all the functions that call it. Here we go. Here's the implementation of memset, right? So there's a file called liba-memset.o that is built somewhere, probably out of a liba-memset.c file, right? And inside here is a whole bunch of stuff, including memset. So this is where the memset function is really defined. And inside you can see that it has some labels and stuff of some local variables and things that it has inside of its little executable over here. I throw all this in here because if you really want to look around and see what's going on, this is how you inspect these files. So the other one is then libgcc.a, which I happen to know is not in the same directory at all. So we're going to have to go and do this again and say, where is libgcc.a if you really want to look at it. And it helps if you spell it correctly. And it comes back and says it's right here. And you can see it's actually coming from a different place. It's still in the install directory, but it's in a different place inside there. So again, if we do a name on that file, pipe it into less, we're going to see a whole lot of other stuff that the compiler has. Now, these are really messy to look at, but if you can see what's going on, every time it says, hey, there's a file here, something.o, there's a little colon. And then it says, here's all the symbols from that file. Now, I don't even know what all this stuff means, but clearly there's a lot going on in there. There's even a main. I guess if you don't provide your own main, it would have a main. Now, this is actually double underscore main, I guess. Not just main, is certainly from some program, but it doesn't have a symbol in it called main. So I honestly don't even know what that thing is. Beats me. And there, now here's where it gets interesting. See what absolute V SI2. What this is because we don't have any math instructions in RV32i. Right? Think about that. How do I multiply two numbers? I don't have a multiply instruction. So in the GCC library, you're going to see a bunch of stuff that looks like this. Okay? And it's going to have multiply, and it's going to have, here's a divide of some kind. Now, like I said, for each file that's in this library, it says, here's the file name, colon, and then here's all the stuff that's in that file. Okay? Now, the file names give you a lot of a clue as to what's inside here, like double underscore abs v die 2 is the global symbol here that is a function that the compiler may call, and it matches the file name. So I can do this, is my point. Rather than looking at the whole thing, I can say, just show me the lines that have a colon in them. This will be easier to read. Okay? I don't need to see all the labels. I just need to see the names of these files, because I know the name of the file is basically the same name as the function that's inside this file that is being provided by this library. Now, I happen to know that because I've been through this many a times and compiled lots of compilers, and I know how the libraries work. But this is a really handy way to take a simple look at all the stuff that's in those files, and you see all these things in here that represent multiplication, subtraction. I don't know what VDI means, but it's probably like a double precision floating point number, how to negate something. I don't know, CLZ. There's like a multiply, all kinds of different kinds of multiply and divides. And and stuff like that. Here's a mod, probably a div mod. So there's probably like modulus division or some other thing, div, I don't even know what this means, but it doesn't matter. These are all the things that the compiler might need to do. And it makes a lot of sense because we don't have floating point instructions. We don't even have an integer division. This is probably an integer division, and there's probably a mul in here somewhere that's an integer multiply. Here's a mult. F3, F2, again, I don't know what these mean, but I know for a fact that we need to be able to do these types of things with our compiler. So, all right, so back to where we were at. In order for this to run, it needed a memset. Now, why did it need a memset? Do you even know what memset is? If you don't type memset is a fill with a constant byte. Okay, so why in the world would we be doing this in the main? Well, it's because we're going to put these first 3 characters in this array, and then the other 97 bytes, we'll find the compiler is going to memset all the rest of them to 0, okay? Rather than inlining the code with a little loop, which it could do, it's just going to call a subroutine to do it, all right? So let's go ahead and rebuild this and make sure everything's cool. Let's look at prog.list. Let's see what's going on in here. There's the CRT0. Here's the main. Here's it calling memset. If you unravel all these instructions, you'll see that it's going to have to create, put some values in. This is the argument 0, argument 1. So what's it really doing? It looks like it's putting whatever x2 plus 16 is it going to go into the first argument to memset, which I think is the address of the thing to fill in. The second argument is the byte that it's supposed to put into memory starting at the first argument. The third argument in x12 is this 96, which, as I said before, remember is the rest of the bytes that need to be filled in. Now, I said 97, and this is only going to do 96. Why? Well, look what's happening up here. When it first starts putting the 1, 2, 3 in there, it doesn't just poke them in one byte at a time. The compiler's smart enough to say, look, I know I'm in a little endian machine, so I'm going to just do this and put this into X15 and store an entire full word directly into this, the beginning of this array, which must be at 12 bytes into past X2. And remember, X2 is the stack. Okay, so I'm kind of going backwards here, but what is it doing here? It's going to subtract 128 from the stack pointer to make room for our stack frame, our activation record. So what's going to go in there? Among other things, it's going to call subroutines. So you can see it stores X1, so it can get X1 back down here, okay? And the last thing it does down here, let's just ignore everything in here for a second. You can see it move X2 back up by adding a 128 back on to X2 to fix the stack where it was originally before it returns, okay? So among other things, what else goes in here? Well, obviously, our 100 and decimal byte array needs to go in here as well. So in here somewhere, the 100-byte array must start at 12 bytes off of X2. It doesn't need to store all this in separate registers as long as the compiler keeps track and remembers where each of these things are. So this strongly suggests that our 100-byte array starts at 12 off of X2. That's why 16 off of X2 is where it says start filling in here, and it says 96 instead of 97 because when it stores an entire word, this word includes a 0. Okay, so one of the elements, because remember, it's going to get stored in little endian order. It's going to get a 01, 02, 03, and what's to the left of this but a 0. Okay, so this is the compiler optimizing stuff for us, right? And he's the guy that called memset. This is why we needed to add the libraries and play all those fun games. Now, after we're done calling memset, we want to call myfunc. So remember, what does it pass to myfunc but the address of the array? And we've already kind of figured out that the array must start at 12 off of x2 because of what happened up here. So this is overwhelming evidence to confirm that hypothesis, that x2 plus 12 is stored in the argument 0 register, and then the OAPC and the jailer pair together is how we call a subroutine, all right? So what is he doing in this particular listing? It helps you figure out that, oh, by the way, the intent of this jailer is to call myfunc and these pair of instructions here. And this all makes perfect sense. So this is the myfunc. It's going to do its thing. When it's done, it's going to return its sum in x10. But remember, main didn't do anything with it. So main is just going to throw it away. And then we get back down to here. We already looked at that. This gives us our x1 back out of the stack, fixes the stack, and goes back to wherever we came from. All right. myfunc, we don't really need to look at the assembler in here. It doesn't really matter. It does what we said. It's going to put a loop in here. We should see, here's our branch if not equal, back up to myfunc plus 10, which is going to be at address 9C. So this is the body of the loop that probably adds all this stuff together. You can certainly see an add 1. This is advancing the address to the next byte in the array, and here's the adding probably of the value from the array. What's going on here? Why is he adding x14 to this? No, I'll leave it as a test to the reader to figure out what the compiler is really doing. It looks like it actually fetches a byte here, and then it adds it down here, and then it fetches the next byte here. Because remember, this while loop ends not because some counter expired, but because the value that it got out of the array became 0. And that's probably what's going on here with this branch down here that's going around this loop, okay? So I'm going to trust that the compiler actually knows how to build a code that works and just say that that just adds up the values and returns them. Now there's this libc init array, and there's some other stuff going on down here. God darn it, that means I lied to you, but I'm not going to go back and fix this video. Here's one last thing that I did add. So I lied earlier. I said the CRST0 has not yet changed. It did change. In order to use the standard C library, we have to initialize that library. Okay? Now, it turns out that I happen to know that this particular version of the library doesn't actually do anything with this initializer. It's going to return right away and not do anything. It's sort of like when our loop up here was supposed to clear out the BSS, but there was nothing in the BSS, okay? Now, we're supposed to call this to initialize the library, so we are going to call this. And the reason is not so much to initialize the library, but to initialize your own code. In C, there's a way to do things that are sort of like what happens in C++ when you have what's called a global constructor. If you create an object that is a global variable, it needs to be constructed before main starts running, is my point. This is the C equivalent of that. Somebody somewhere has to call these constructor functions. That's what this thing does, okay? I left that out, my bad. So I'm sorry about that. I'm not going to go back and fix it. That's a small enough thing to toss in here. I think we're good. Anyway, so what are we going to do now? We're going to run this thing. And it's going to work fine and dandy. Now, this is going to be doing a lot of stuff with the initialization of the library and all that other fun stuff. Let's see if it works correctly. It terminated by an e-break at address 48. That's pretty tiny. That's probably in our CRT0. And we can also recognize that this is the end of main because I was just looking at what it does. It loads X1 from there, and it adds the 128. So this is actually definitely the main, finishing and returning. Now, what does this thing do with what it did with the values? So what's going on here? It's going to actually return the sum. So when this thing is done, it should be 3, 4, 5 plus 1. It should have 6 in X10, right? So this is a lot of rigmarole just to have a 6 and register X10. So there's X8, 9, and 10. Yes, and you can see that there's a 6 in there. So that suggests, anyway, that the program is working correctly. Now let's figure out that it got the things in the right place, right? What's it doing? It fills out this array. It's got these data. Here's the memset function. You know what? It doesn't do anything with these at all. All we need to know is to make sure that the BSS was initialized right. We already know that that happens. So in this particular run, there's where it ends, and we go down to 1,000. It should have zeroed out those. There's the array, and there's the single variable down there. Now, if we go to the end of this file, look what we see down here. Remember, this is where the stack is. Remember, the stack starts at 3,000 and hex works its way down. Look what we got. We have an array of all kinds of 0 bytes in here. The first 3 elements in there we recognize as the 1 and the 2 and the 3. Now, this is coincidental, right? When you have an activation record, you know, anything could happen. But we were looking at the code. We know what main did. We know that main called this subroutine, myfunc or whatever it was, to add up these values. Myfunc didn't really do much, so it probably ran entirely with registers. If we really look at the assembly language from the compiler for myfunc, we'll probably see no loads and no stores anywhere in this code. This is entirely executing using the registers. It calls no subroutines, so it never has to really save any registers that it needs to get back later. Okay, so that's actually pretty cool. And which is why, by the way, you don't see anything down, you don't see any of the other garbage down here that suggests that there's an activation record in use by that myfunc down there. Again, when you get down to these subroutines that don't need to ever access memory, they're going to run really fast because they're only using registers, okay? So this is our 100-byte array that probably ends over here somewhere, sitting in the stack for main. All right, so we recognize everything. It all looks good. Now what's wrong? How come we have 2 more of them in here? Well, we haven't done every last thing we need to do. Remember, I forgot to call the libc init. If we're actually going to use the libc, which we did for the first time in stand 8, we need to do that. So in this crt0.s right here, we should see it still being done right there, okay? And what else is going to happen in here? So let's go ahead and build this one. This one is supposed to die. And how does this one die? Well, we're going to compile it, and it goes along, and it says, oh, we got another mystery in here. What the heck is this sberk thing? Well, remember where the program break line at the end of the heap is? Guess who has to handle the heap? We're not quite done dealing with our address space just yet, are we? No, we are not. Okay, so why does this one not work? Look what happens in this main. I want to malloc some memory out of the heap. That's the call to do it in a C program. Give me some space. I want a hex, 100 bytes. All right, that's 256 in decimal. Then I'm going to call stir copy, and I want to put hello world into that buffer that I just malloced. Okay, then I'm going to call myfunc and save that return value, and we'll see that myfunc is the same one in the as we did before. This is just a modification of the earlier program, so we're still going to sum them all up until we reach a null character, which in the case where there's a string, the string will have a null character at the end of it anyway. So this is going to add whatever the H code and the E and so on together, and it's going to figure that out. Now, when it's done with all that, I'm going to free up the memory out of the heap, and I'm going to return the sum of all these characters. Now, yes, I could have just said myfunc and put a literal in there. It would have been a whole lot easier, but the whole point of this is to show you that malloc is not working. So in order to write a real C program, you need to be able to manage the heap. So what are we supposed to do? Okay, now if you read all the documentation about how newlib is supposed to be used, you'll find out that in order to use newlib, which is what's giving us our standard library. Okay, new lib is merely just a distribution of somebody that wrote a version of all those standard library functions. Okay, and those standard library functions will work, but some of them need some subroutines, right? Just like the standard library calls also might need the compiler library calls, the standard library calls also need these stub routines. So if you read the documentation for new lib, it will tell you that in order to function and to be thoroughly and to use any of the functions in there, you need to provide a certain set of routines in place of where an operating system would be. Remember, we're not running with an operating system. Normally, the operating system will provide a bunch of subroutines that all these libraries can use. Without a subroutine, we got to provide them ourselves. So let's look closely at what these things are. Again, you read the doc, it says do this up here. This is all kind of boilerplate. And they actually literally give you all these functions here. If you Google around enough, find the right doc for the actual library. It says you need to have an underscore exit that will, do an exit, whatever that means, right? Now, if you have an operating system, it'll terminate the program, clean up the address space, throw it away, and go back to the command prompt. Well, for us, we can't do that. So what I'm going to do, this is actually called an inline assembler instruction. I'm going to call eBreak right here. So if you call exit in their library, it's going to come over here and call underscore exit, and it has a parameter, right? The exit code. I don't care. I'm going to just do this. This is how you put an inline assembly and language instruction in a C program. Just say eBreak. That's all it'll do. So if you say exit, it's going to eBreak. Okay? What happens if you call kill? Again, it says, you need to provide these functions. Well, kill is the command that you use to send signals to other processes. And by default, what they said to do is put a spin loop in here, an endless loop. Well, that's worthless to us. That's the same thing as killing the program. You could also just return from it and ignore it. I mean, there's plenty of things you could do. It depends on what you want to accomplish if you decide to actually call it, which really is irrelevant without an operating system. There's really nothing for kill to do. So I just said, well, I'm going to just eBreak, because if anybody calls that, it means that they've screwed up anyway. Now, there's other functions in here, like give me the program ID number of the executing process. Well, there's only one on this system. You'll never be able to call fork, for example. You can't create new processes with this simple library and no operating system, all right? So the only process that's running will have a process ID number of 1. So if you ever say get PID, you'll get a 1. Now, you have to provide these file operations, okay? You got to be able to open it and close it and call fstat and some other stuff. You may have never called these before, but clearly you've opened and closed files before. And at the bottom layer, the operating system has to be able to do something like that. Well, I'm not, as you're going to see, I'm not going to allow you to open any files because we don't have a file system. We don't have any disks or anything. So as long as you never open a file, you never have to close it. But if you try to close it, I'm going to return an error, and I'm going to set the error node to bad file and so on. If you ever call fstat on a file, well, that's fine and dandy. I will stub this in and just say that the mode of the file that you're asking me about is a character-based file, and everybody's happy, all right? If you ever ask if some file descriptor, remember this is a very low-level call. He says, "Tell me about this file. Is this file a TTY, which means is it a console? Is it a window like the one I'm typing in right now, or is it like a regular file on a disk or like a socket talking on the internet or something like that?" But if you ask is it a TTY, which means it's a terminal, I'm going to say yeah, it's a terminal. Why not, right? If you ever lseek in the file, I'm going to say yeah, that was fine, sounds good, return 0, everything is fine. Now, along with the close, if you ever try to open a file, I'm going to just say, the system-wide limit on the total number of files has been reached, right? And in this case, that limit is 0. In other words, you can't open this file. Why? Because the operating system can't do it for you. Why? Because there is none. You try to read from a file, I'm going to just say, okay, that's great. It's an end of file. There's nothing to see here. You ever try to write to a file? I'm going to say, okay, sounds good, and I'm going to completely discard all the data you gave me. Just don't do this stuff. And now we get to the important thing. This is this SBRC thing that was missing in standalone number 9. If you look at the doc and you look at what this thing does, it's actually quite a simple little function. What it does is it says, if you want to move the you want to set the break, okay, is what this is, set the break line, the program break, where the heap ends, and it's going to give you delta. Notice delta is a signed integer, okay? So if I say I want to allocate memory, and there's no extra space in the heap right now, and honestly, right now the heap is completely empty in the main routine because it's never had, no one's ever allocated anything out of it yet. I initialize, okay, the end of the data, the current end of the heap that it's kept track in this function, in this file with this, non-global variable. I'm going to remember where the end of the heap is, okay? And I'm going to initialize that to this _n symbol that I get from the linker. And because it has to be declared somewhere, I'm going to just say, well, I'm going to assume that it's a character array, okay, which is fine and dandy. That's one way to introduce a symbol into a C program that something somewhere else is going to make available, right? And I'm going to just say it's a character pointer. It's really handy for me to do that because if I add 1 to a character pointer, it goes up a byte. And if I subtract 1 from a character pointer, it goes down a byte. And that's what this delta value is here. So this is going to be a really nice data type to lie to my C program about this label here. It really is represents the address of a character array, so it's okay to do this. Okay, so what do? I say, well, remember the current value of where the end of the heap data is. Probably should have called this end of heap instead of end of data for more readable, variable names here. But I remember where the end of the heap is now, and then just add the delta to it and adjust it as requested, okay? And then return this pointer value. So when you call sbreak, and then sbreak calls this _sbreak, what you're really saying is, change the end of the thing, where the heap is, and then tell me where it used to be. That's how this function works. So if I say sbreak, and I put a delta value of, say, 128 bytes, this return value actually tells me where the 128 bytes that I've just asked for begins, because it's where the old end was. Okay, so all it's going to do is move up the end of the data by what I asked for and tell me where it used to end. So that's what's going on in there. And that's what the documentation here talks about, right? So by putting these functions in here, among other things, I solve my sbreak problem. I can now compile this. Let's go ahead and do that. Okay, it worked. Okay, let's make sure that it's still doing the same thing that it did before. And I'm not lying, right? So here's my myfunc. It still does the same thing we saw before. And here's my main, all right? It mallocs it, and it remembers how much, it remembers the sum that it gets back in myfunc, frees up the stuff out of the heap, and then it returns the sum. That's all it did before. crt0.s is still the same, complete with our little init array that we had to add because we're going to use the C library, all right? So let's go ahead. I think I just did a compile. Well, let's do another one anyway. To then look very closely. Again, we're going to use these libraries. And because my main calls malloc, and malloc needs to move the program break line, that's why we have to have that sbirc in there, okay? That's on us. Unfortunately, the new lib doesn't support that for us on our behalf. So let's go ahead and run this. Here's our final example here. Oops, terminate, not template. All right, so what happens here? I'm getting a little giddy. We ran, as usual, we see the main ending with the jailer to here and going back to e-break at address 48, which is sufficiently small. That must be inside of our CRT0 if we track that down. I'm sure that's the case. Now we got a lot of code in here, right? We brought a lot of functions in here and malloc and all this stuff. So look at how big the text region is right now. Oh, look what happened there. I just saw a hello world go by. Among other things, where do you think it copies the hello world from to initialize that that variable, right? Because remember, it's going to probably call it like memcopy or something. So it has to copy it from somewhere. So among other things, in the text region of this program is going to be basically a literal pool. If you write mainframe assembler, you might remember you write ltorg every now and then that says, any of the inline literals that I've used, put them here. Well, the compiler does the same kind of thing, and that usually comes at the end of the text region. So we can actually sort of see them in here. Here's our hello world, and then there's a bunch of padding to get over to the BSS. So before we play around with this too much, let's see where everything is. Why? Because notice that I took away the WL with the -T data. I no longer tell the compiler where to start the data. I say, you figure it out. You know why? Because there's too much text now. Look at how much junk there is in here. I can't just say start the text at 1000 in hex anymore. Because by the time it gets there, there's a bunch of other junk in the way. All right? Actually, it doesn't look too bad. Maybe it could. It depends how big this thing is right here, but that's actually way up near the end. Let's run it again. Well, what's going to happen is all those literals and junk are going to be in there. Yeah, you see what happens? It goes just beyond 1000 or at 1100 before we get done with all these literals. So I can no longer say, -T data equals 1000. I could have set it to 150 or something like that, assuming that these zeros are not part of some literal or something like that. But by not doing anything at all, I just said let the compiler figure it out. And what it does is it gets to the end of the text region and just leaves a hole, moves it forward, and just says, okay, I'm going to start it here. It usually starts at 1000 past the end of this thing. So it probably ends at 1128, which is about right. It moves itself up to 2128. And it says, here's where the data begins. All right, look at all the crud in here now. Init array end, init array start, blah, 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 blah. And we see all kinds of stuff in here about malloc, sberg, threshold, BSS, start down, and more malloc stuff in the BSS. More malloc. So malloc has a bunch of variables that it needs to do its job, obviously. Some are stored in the data region, some are stored in the BSS. Here's the B2 and the B1 arrays that we don't use that are sitting in our main, as well as the other stuff that malloc put in there, right? So when we run this program, what's it really going to do? It's going to add up the value of HELLO space WORLD, and it's going to return it from the main, ultimately. So let's look and see what's happening in here. Here's X10, 41C. I don't know, we'd have to add them up by hand and see if that's the case. Maybe that's a reasonable number to think it might add up to that, because some of these are pretty big values. The lowercase numbers have values that could go up to like 70 in hex, and there's about 10 letters, so it could quite easily be add up to that number. That's a perfectly reasonable thing to expect to happen down there, right? Now, if we look through here at the stack and scroll all the way down to where the main is, all right, we no longer see the array down in here. Right? Well, why would we? We didn't put it on the stack like we saw in the earlier example. We put it in the BS, or rather, we put it in the heap is where it went. So the heap starts where? Well, the heap starts right where the program ends. So if we look for 29B8 and we run it, we know that the address in the hex dump would start with this number here. The caret means on the far left side of the output, the beginning of a line that starts with that number, which is, more specific than just searching for it anywhere, because it could show up in various register values, and we'd be searching through the executable instructions as well as other things. Well, lo and behold, 29B8 starts right here. It's the end of the memory. So we see some garbage, or what appears to be garbage in here. Then we see the hello world and the null at the end of hello world. So when we called malloc, what did it do? It moved the program break line down. I don't know where to. Down here somewhere. Okay, we see some garbage down here as well. We see a 541. We'd have to go look at the source code of malloc to see how it works, to really understand what it's doing. But when we allocated this array for hello world, how big, what did I ask for? I think I asked for a hex 100. Right? I did. So I asked for 256 bytes. Let's go ahead and run this again. I forgot the darn address, so let's go back. We'll be able to find it again because it'll say hello world in here somewhere. Oh, there it is. Okay. So here's where it says hello world. Well, these bytes here are part of the heap. And malloc, I happen to know, keeps things in memory before. When you say malloc something, it says, okay, here you go. Your thing starts at 29C0. I happen to know there's a header in memory that comes before that. Okay, this may have to do with how big it is and things like that. Okay, it's obviously not the exact size because clearly 649 is not the same thing as a hex 100. But if we look here at 29C0 and we get to 2AC0, this thing would be the end of the array right here. And look what happens. You see there's a little bit of garbage right here and some uninitialized stuff before that. Isn't that a lot like this? Okay. Now, if you actually look at implementations of malloc, this is very common. Okay. I didn't look at the one inside of this new lib that we're using, but like I said, I happen to know that the standard way of doing this is just to say back off from the address that you've given the user to use for their data, and put some stuff in here to remember how big it is, and in an indicator that says that this is indeed the beginning of something. And if you screw it up and your program fails, sometimes you get an error message from the runtime environment, from malloc. In fact, you might say freeze something or other, and it might say something like, oh, the headers were clobbered, your program has corrupted its memory. And what it's saying to you is you ruined these values here that you're normally not supposed to use in your program, that come before and or after these regions of memory that you've been allocated by request from things like malloc. And new and delete work the same way. Okay, so by looking at these, what's really happening in the memory, you can actually see it. It's right in your face. Okay, so I asked for 100 in hex. It gave it to me starting here. I put a hello world in there, and I use string copy, so it ends with the null. Why would it know or care to put all the extra and padding over here that no one's ever going to use, right? When I call my func, it adds up all these values. I'll leave that as a task to the viewer to figure out if the sum of all these really is 400 and whatever the heck it was at the termination mark. 41C in hex. Maybe it is, maybe it's not. Okay, so we can go through here. We can see all this stuff. I hit capital G to go to the bottom of the file. And the bottom of the file, of course, these are the activation records for main and malloc and free and all these stuff, that overriding each other. So, God knows what any one of these particular values are, because the stack will go down in the memory and then back up and down and back up as it needs to, as things are called and returned. So this is a complete example of how you start a C program. And this one covers everything, all right? Soup to nuts. If you're using the new lib, okay? You got to initialize things. You clear out the BSS. You're supposed to initialize the library by calling this libc init array. You call the main routine, and when the main routine is done, you're actually supposed to clean up. There's like a finish and shut down of the array and some other stuff. I don't care. When main comes back, I just want to halt right away. We're not going to clean up any library stuff. If you want to do this, you want to be thorough, go ahead and read the doc on how newlib works. I think it's called fini init array or something like that, and that will undo anything that has been initialized up here at the beginning. Then you could call eBreak, and that would be a little bit more formally correct. So if you look around on the net for CRT0 examples and runtime startup examples on how to call C programs on RISC-V, you'll basically see exactly this, followed by perhaps one more call down here to clean up things before it goes on its merry way. I'm just not cleaning up because there's no point at that time. The other thing you're supposed to do, and you can probably find this around on the internet, is implement all these little stub functions. And you can actually do these for real if you want to. If you actually create a simulator that has a simulated disk and some other stuff, knock yourself out. You can actually open and close files and everything. In fact, if you wanted to, in your simulator, you could actually open files that are actually files on your system, so that things that are running on the simulator could actually open up files that are in Linux if you really wanted to. If you wanted to do that, of course, you can't just write open and close in here, because remember, these are actually running inside your simulator. If you wanted to do that, what you'd have to do is use something like ecall, right? Remember, there's a in our VLP document, we've been using eBreak to stop the simulator. You can also use ecall if you want to do anything you want. Quite frankly, this is supposed to be used to call operating system functions. In your simulator, you can simulate the operating system if you want. You can execute ecall, and when you do so, you can decide whatever convention you want. You can do things like set, register A0, A1, A2, A3 to any number of arguments and things like that. And when your simulator gets the ecall, and you decide you're going to do whatever it means to execute an ecall function, you can actually do anything you want in Linux to make it happen. So you could actually read files and stuff like that, and copy the data that you read from a file from your operating system into the simulated memory as you wish. So you can do things like that, and there are simulators that are written that way, and that's kind of neat. We could keep that for a future assignment in some other class. We're running out of time, so we're not going to do that, okay? So this is how you get a C program running, and you do it properly, and you satisfy the needs of the library, okay? And when things fail because these are getting hurt, it's like that old joke. Doctor, it hurts when I go like this with my arm. Doctor says, don't go like that. So what does that mean here? Don't try and read and write files. Okay, why? Because there aren't any. Don't try and do these other things either. That's all file I/O. This is innocuous. If you ask what your process ID is, it doesn't really matter. Don't call kill to send signals anywhere, because we don't have signals and there's nowhere to send them. So that's just pointless. You feel free to call exit if you want, because that'll just simply call eBreak. But this is all you got to do. Okay, these are all the parts to calling a C program. So if you're at NIU and you have a login on Hopper, well, this is where I copied them all to. I'm going to go ahead and make clean and delete all this stuff. I don't really care. What you want to do is you want to copy the stuff from here. You don't want to copy this executable because that's irrelevant. What you want to do is copy these example files, like you saw me do. And I'll make sure that I've cleaned everything out so you don't get extra garbage in there. All right, so you want to take this directory right here and just copy this to somewhere else, like you saw me do earlier up in my home directory when I said copy blah, 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 recursively, right? So it was CP minus R, right? So remember this last time, CP minus R, all of this, and then I typed XXX. That's how I created this directory right here, and then made copies of all these example files in them. And this is what we've been hacking on and tinkering with for the last hour when I talk about these standalone programs. We can talk about these at another time. These are actually going to be multi-threaded applications. So if you made it this far, thanks for watching. Hopefully you're watching it at double speed or something like that. I'll see you on the internet.